So welcome to the deep dive for Unit 2. Unit 2 is about linear equations. So before we begin, I just wanted you to remember from the last unit that y just means the answer or the output. So does the notation f of x, where it's f with a parenthesis that we read it as of, and then x. And that this is just a more fancy notation to mean the answer or the output. So this is the same thing as y. So in a table, for example, sometimes you put x and then y, but it doesn't have to be a y because it could be an f of x. It doesn't have to be f. Remember, it could be g or j or r. The letter in front's just the name. But yes, remember these two mean the same thing. So, to talk about ways that we can take the math that we learned in this unit and make it harder. First of all, linear equations are only one type of equation in math. You've learned this first unit's about linears, but there are tons and tons and tons. And for all types of equations that you learn about, they're going to want you to go between the four representations. So it's called multiple representations because there's multiple ways to represent all mathematical things. You can put them in tables, you can make equations out of them, you can make a graph out of it, and it could all relate back to a real-world situation. Linears is the unit that we're on. Unit 2 is all about linear equations. And linear equations are a specific type. Their equations always look like y equals mx plus b. Remember, I could replace the y with an f of x. So in this equation, you've learned that the shortcut is that b is your starting point or your y-intercept, and that m is how much you're growing by, also known as your slope. So the reason why this equation works for linears is because what it means to be linear is that you're either adding or subtracting the same amount each time. So let's say every time you get 3 more. So after one time you're at 3, but then after a second time, you have to add 3 more. And by time number 3, you have to add 3 more. And by time number 4, you have to add 3 more. And by time number 5, you have to add 3 more. And 3 plus 3 plus 3 plus 3 plus 3, adding 3 5 times is the exact same thing as taking 3 and multiplying it by 5. Which is why our growth, our m, would have been 3, and how many times have gone by is what you times it by, because multiplying tells you how many times you add up that number. So since you're adding the same amount on each time, or you could be subtracting it if it's negative. When it's the same amount each time that gets added or subtracted on, it means it's growing by a consistent amount. So in the table, for each time, which is x, that goes by, the amount, which is y, will change in a consistent way. Which just means you are either adding or subtracting the same amount for each time. So then linear equations, when you put them on a graph, they always end up making straight lines. Like if you work here, this is a linear because here's your mx plus b part. Actually, I could put an m right here and add a slider, and then put a b right here and add a slider. And I can slide around, like my b moving up and down takes my line up and down, and then changing my m changes the slope and the steepness of that line and what direction it's going in based on the slope. Because if it's positive, it's going to be going up like this, versus if it's a negative slope down here, it goes down in the other direction. And then moving b around moves it up or down. So changing b only moves it up or down. Changing m just changes like the steepness of the line and the slope of it. However, it's still a straight line. Not all equations make straight lines because everything in this world that we have can be represented by an equation. For example, a basketball has its own equation, and it definitely doesn't look like a straight line, like the outside of that basketball. It looks like a circle, because circles have their own type of equations. Absolutely everything will have its own type of equation. So in math, you're gonna learn about all of them, but linear specifically makes straight lines. And in a situation, you know it's a linear situation if, and it's the same thing like the table, for each time that you do something, or that goes by, your change in amount, like how much you have or how much the situation has, is the exact same. And another word for the exact same is consistent. So this is specifically what makes something linear. However, in the future, you're going to learn how to do this for all types of equations out there, for circles and all the other ones you don't even know about yet. So let's talk more about linear specifically. With linears, they have a consistent rate of change. And so rate just means how much, and then of change is like how much you're changing by. So another word for your rate of change is slope. So on the test, if they ever say what is the rate of change, what they're asking is what is the slope. Remember, what slope means is the change in how much you have divided by how long you took to get that. And that's going to tell you then how much you're getting or losing each one time. So an example of this might look like this. You buy a flower that's 3 centimeters tall. By day 6, it's 7 centimeters tall. And 12 days later, it's 15 centimeters tall. Well, to begin with all of these, you're going to want to ask yourself, what is X and what is Y? Well, X is usually time, and in this situation, the time they're talking about is days, because they keep using the word day. And the Y, the amount, is how tall the flower is, flower height, and it's in centimeters. So it's okay if you just wrote cm for centimeters for the Y value. So I'm just going to quickly make a table about this situation. Let's see, you buy a flower that is 3 centimeters tall. So that's the centimeters, the Y, the amount. And for days, it's after 0 days because you just bought it. However, they're saying by day 6, it's 7 centimeters tall. And then 12 days later does not mean day 12. 12 days later means 12 days after the 6 they just talked about. So you do 6 plus 12, which is 18. So on day 18, it's at 15 centimeters. Your goal in figuring out your slope is to figure out how much height the flower is getting and how long it's taking it to happen. So it doesn't matter if you do it between day 0 and day 18. It doesn't matter if it's between day 0 and day 6 or between day 6 and day 18. You can pick any 2 days to do this with. And the formula to figure out your slope is you're going to pick one of your points to be your first point. Like let's say, oh, I want to do it between day 6, so I'm going to make this my first X, which means the 7 centimeters will be my first Y. Then I pick a different point. I could either pick the first one or the last one to be point 2. I'm going to go ahead and go with the last one. So this would be my second X, and this would be my second Y. So to figure out the change between 7 to 15, I'm going to take the 15 and minus the 7. So that's the whole y2 minus y1 part in the formula, is you take the second one and you minus the first one to figure out how much it's changing by. And 15 minus 7 is 8. Then, so it's going up by 8 centimeters. But how long did it take? Well, it's day 18 for the second x minus the first x was on day 6. So from 6 to 18, to figure out how much you go up by, you can always do 18 minus 6 to figure out that you're going up by 12. Which means altogether, we're going up 8 centimeters in 12 days. So if I do 8 centimeters divided by the 12 days it took, I would find out that the slope is 0.6 repeating for a long time, which you can always do 0.6 and then round up the next number to 7. So that's if I did it between these 2 points. I also could do it between 0 and 3 and 6 with 7, because from 0 days to 6 days, that's going to take 6 days. And then 3 to 7 is 4, which means I'm going up 4, dividing by the fact that it took me 6 days, and 4 divided by 6 is also 0.6 repeating. So it doesn't matter which days you do it in between, you'll still get the same answer for your slope. That in one day, each one day, it's going up 0.67 centimeters. So that's the meaning of the slope. In one day, the flower grows 0.67 centimeters. So then if I had to make the equation for this, just so you remember, it's y equals the slope, x, plus the starting amount. And this time the situation did give me the starting amount, saying on day 0 I bought it at 3 centimeters tall. So you do plus 3. If you didn't know that and they only gave you these 2 points, remember you'll have to do the whole plug in one of the points to solve for the b to figure out what it is. And then they're going to always expect you to be able to graph these linear equations. So if I come to Desmos, this specific one, the m was 0.67 and the b was a 3. And this is my graph. Starts at 3. And each one, it goes up 0.67. So that's at 1, 3.67. Now here's the thing about graphs. On the test, they are going to tell you to make sure you have appropriate scales, proper labels, and a title. Let's talk about what each one of these means. Appropriate scales means that your tick marks are good. So whatever from 0, whatever you make the first tick mark worth, like if you say this is 1, the next one has to be 1 more. It always has to be the same, but you don't have to go by ones. You could go by any number you want for the x's, and you can go by any number you want for the y's, and it doesn't have to be the same as the x's. For example, on the y-axis, I can choose to make the scale go by 5 instead. And so then my graph could look like this. And note, by going by 5s, 5, 10, 15, 20, 25s on my y-axis only, it allows me to go all the way up to 25 and only 5 little tick marks. And so let's say I didn't want to graph the equation, but I wanted to graph instead the table that they gave me, like the 0.03, which is right there. But then there is also the point at 6, it was 7 centimeters. And right now, this point's not on my graph. And it's because on the x, I only go up to 5 right now. So I can change the scale for my x's. So if I go by 2's for my x's, see each x is now worth 2, and so 2 more is 4, and then 6. Now that point's there, the 6, 7. But if I want to get the next one, 18 with 15, and I only have 5 tick marks to do it, 1, 2, 3, 4, 5. Then if I want to make sure my x's go all the way up to 18, and I only have 5 tick marks to do so. An easy way to figure it out is that if I know I want to go all the way to 18, but I only want to use 5 tick marks, I can do divided by 5 and figure out they each need to be worth at least 3.6. Now going by 3.6 would be weird. So either go by 4, because more, you want more than enough, but not too many. So going by 4 works, or going by 5s work. 18 goes with 15 for the height. So if my y-axis, I only need to go up to 15, going all the way up to 25, that's too many. I don't need to go that high. So I don't need to go by 5s for my y-axis. Let's see. I want to go up to 15. I want to use 5 tick marks, so divide that by 5. And find out that I could go by 3s and still hit that point. So in order to fit all 3 of my points into my graph, and only 5 tick marks on each side, I decided to take my x's by 4s. So here's 4, 4 more is 8, 4 more is 12, 16 and 20. And that makes sure that 18 got in there, this point here. And then to make sure that 15 got in there, I went by 3s on my y-axis. It doesn't matter what you choose your scales to be, as long as you do it properly. Where if you say this first one's worth 3, each one's only worth 3 after that. Then to put a point like this, 6, 7, well, 6 is somewhere between 4 and 8. It's right in the middle. And 7 is somewhere between the 6 and the 9, and it's a little bit closer to the 6. So you sort of have to guesstimate where that point is. And then the same thing here, you know the 15's on this 15 line, but the 18 is right in the middle of 16 and 20. So you sort of have to guess and estimate well where that one is as well. And then you could connect your dots after that. So this is what they mean by appropriate scales. If you're graphing from the equation, you don't need your scales like this. If your scales were by 1s, if your scales go by 1s for this graph, where each one's worth 1 tick mark, when you graph it from the equation, you just need to start at 3 and then go up 0.67 from there. So you don't need your scales to be any different than each tick mark is worth 1 if you're doing it from the equation for this guy. Versus if you're doing it from the table, you did need your scales to change. Note that I also decided to only use 5 tick marks. I could have used as many as I wanted in each direction. So it's basically up to you. So as long as you do it properly, it's fine. So that's about the scales. However, for labels, they want you to label what the x-axis is about and what the y-axis is about. What was the x-axis about? This is a situation that involved how many days went by. And what was the y amount of that? The y was the height of the flower in centimeters. But I'm just going to say this is about centimeters, because it's how many centimeters you have. So now I've labeled both sides. And the title of the graph is just what it's actually about. So this graph is height of a flower. So on top, that's what it's about. It's the height of the flower, the heights in centimeters, and then we're talking about after how many days. So your graph would have to look like this for you to get full points on the test, with appropriate scales, labels, and a title. Finally, there will be scatter plots on the test, and they make it a little bit weird by adding on some more data and changing the line of best fit. So I have an example scatter plot that is going to compare how many items somebody sold and how much money they have in their bank. And let's say that data set A is kids data. So a bunch of kids in the neighborhood started selling things. So when you start selling things, first you have to borrow money from somebody. Like you have to ask mom and dad, like, hey, can I borrow $20 so I can go get some lemons and some sugar and make lemonade? And then once you start selling the lemonade, you start having to pay your parents back first the money you borrowed. And then once you've paid them back that $20, you start making money. So let's say kids started making things like lemonade and bracelets and other things to make money. And this represents their data. So some kid sold 6 of their items and now they have $5.5, so $5.50. And that's their piece of data right there. And a different kid sold 10 items, and now they have $8. So that's their data point right there. And all of the data points got put there, and now you're asked to make a line of best fit. So the cool thing about using Desmos, which you're not allowed to use on the test, but I can use it to show you, is if you do a y equals mx plus b and then add a slider for m and a slider for b, you can take this line and like move it around. So I can move it up or down to try to get it in the middle of the points. I can change the slope. So I like changing the slope first to try to get the shape I think it looks like. Like I think it's kind of angled like this, most of the data. And now I'm gonna move it up. So I still don't feel like if I were to draw a shape around this, that the line's doing exactly what the data is doing. All right, this seems to be doing sort of what the data is doing as far as starting-ish down here and moving up in the middle of the points. Let's make sure it cuts it in half. So on top I have 1, 2, 3, 4, 5, 6, and on bottom I have 1, 2, 3, 4, 5. So that's close to half, so that's good. So this is claiming that most of the kids on average are starting in debt by $1.80, and that for each item they're selling, they're making about 90 cents. 0.9 means 90 because you can add a 0 at the end for cents. And so that's the situation with kids. Now, what do you think is going to happen if I were to add adult data? Let's say adults were doing the same thing, and they had to borrow money from somebody and started selling their own items that they're making in their house. Like, let's say they're doing it on Etsy or something. What do you think would happen if I added adult data to this scatter plot? So here's what's going to happen on the test. They're going to give you a first set of data and ask you to create the line of best fit and figure out the equation. So if I put the slope and the y-intercept in the equation down here, here's the whole equation as an equation. Then they're going to say, okay, we're going to add more data and you're going to make a new line of best fit. And so they're going to give you a second set of data, and they don't want you to make a different graph. They want you to add them onto the same graph. So now the ones in black were the kid data, and the ones in purple are the adult data points. However, they don't want you to think about them like they're two separate things once you add them on. Once you add them on, it's like they're the same thing. So I'm going to turn them all black because they want you to think about it as one whole thing. Like now this is our whole neighborhood, all the kids and all the adults put together. This is what we did. So now I need to make a new line of best fit that thinks about all of them together. This line of best fit's almost good. I would definitely say that it's not following the same slope. The slope needs to look more like steeper, and then it has to start further down. Let's see if this cuts it in half now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's just about half and half. And the line of best fit is slightly different. So the slope is 1.3 and the y-intercept is negative 7.2. So this one is this equation right here. So this was the one with just the kids, and this was the one with everybody. And then they're going to ask you, how has the line of best fit changed? Data set A, the kids' data, that was the equation. And then for data set B, where we added the adults to the kids to think about everybody all together, that was the equation. And how they've changed is your y-intercept. The kids only borrowed $1.8 in the beginning, on average. However, it felt like the adults were borrowing a lot more. So when we added them all together, it made it look like on average people were borrowing about $7.2. So by adding the adult data, the line of best fit changes because they borrowed more money in the beginning. And what happens with the slope, when it's the kids, they're only making 90 cents for every item they're selling on average. However, with the adults added in, it's more than that. It now becomes about $1.30 for each thing they sell. So, and they are making more money for each item they sell. So clearly, as a whole, the adults are doing a lot better than the kids, because when you mix the data together, it brings up how much they're making each time. However, they were also borrowing a lot more money in the beginning, the adults were, which brought everyone all together looking like everyone was borrowing more than when you just separate the kids' data out.